Today I am going to talk about advanced SHELXC CDE. So this is a talk that is going to deal with advanced experimental phasing. The next talk is one in Struby and one I'm only giving in Struby because they asked for it explicitly, which is about how to find the right resolution and data format. So it's a more basic talk. But the next one in Diamond is next week, and it's about twinning. And that's a very general lecture introducing the concept of twinning with a look to macromolecular twinning, but it should also be interesting for small molecule crystallographers. And I'm going to bring some examples. So this is the SHELX workflow I have been showing a few times already. SHELX has 3 programs, SHELXC, D, and E. SHELXC does the data preparation and quality indicators and prepares the files. SHELXD finds the substructure, and SHELXE does the density modification. Thank you. I will go through the programs in approximately this order today, showing some new features or some not so well-known things you can do when stuff doesn't work. The first thing I'm going to talk about are SHELXC quality indicators. So at this moment, you should have measured your experimental data set, you've processed and scaled it. So you already have some idea of the data quality from your scaling statistics. Typical output has quality indicators, and you need to use them not to decide on how well your scaling worked, you should have done that before, but merely to decide, are your data going to be good enough for the experimental phasing you want to do? And if so, where are you going to cut the resolution for the substructure search? You have the average of D double prime over sigma, which is an estimator of F double prime of the anomalous signal, and a dispersive signal, if you've got an experiment where you have a dispersive signal, like isomorphous replacement. These values should both be asymptoting to 0.8 in the outer resolution shells, given you measured your data to the resolution limit. Because 0.8 means there's no anomalous signal. And if the value is significantly lower than that in the outer shell, your data processing wasn't quite right. So you should then go back to data processing. So it's one of the first things I look at when someone brings a data set is, does that go to 0.8 or 0.7 would also be all right, but it should not be 0.3. And it should also, if they measure to the edge of the resolution, much higher, but it usually is not so often seen. If the line is missing, or if the line is 0, it means your input data were merged. Friedel opposites were merged. In this case, you have inputted the wrong data set. And you need to go back and find a data set that actually contains Friedel opposites. Then you get CC half, anom. So correlation coefficients in crystallography are usually Pearson's correlation coefficients, and they give you how well data from something agrees with data from something else. Since you're not always having something else, in particular not in a set experiment where you only have one data set, there is something called CC half or self-correlation coefficient. In order to calculate any self-correlation coefficient, you take your data set, you take all the anomalous differences if you do an anomalous one, but for now let's only take a data set. You split it into 2 halves randomly. Then you have 2 pots with intensities. You look how well the ones which, according to symmetry and measurement, should be agreeing, are actually agreeing with each other, giving you a correlation. You do this for all of them. That gives you the self-correlation. A CC half anom is calculating all anomalous differences that are possible, splitting them into 2 pots, and comparing them to each other. Basically the same procedure, but now we're using anomalous differences instead of intensities. And it's a good measure for the anomalous signal besides D double prime over sigma, and should be above 25%. That's about where you can do the resolution cutoff. For a MAD experiment, you can calculate a CC anom between 2 data sets. for example, inflection point and peak. So you've got your data set for the inflection point and the data set for the peak, and you calculate the correlation between them. You also need CC anom for manual multi-crystal averaging. So I don't know if you remember, but finding the substructure is an overdetermined problem with noisy data. So we've got a lot more data, all the intensity differences, than we have actually parameters to search for, which are only the atomic positions. Now, it is nice to get a high multiplicity because that limits your noise, your error, from one data set. But even better than that is to actually merge data from several measurements from several crystals together if the crystals were isomorphous. And this is called multi-crystal averaging, and in some cases can make all the difference between, in particular, sulfur set experiments that solve and those that don't. There is, however, these days automatic programs like Blend by James Foazi to do this automatically. But if you do it manually, you need CC anom. This is a typical SHELXC output. There is resolution up here, infinity, meaning close to the beam stop, and then the data set goes to 1.68 angstrom. We've got a number of data, chi squared, that should be about 1. This data set is very well behaved. I over sigma, which is the average I over sigma in this resolution shell. Completeness, so completeness should be high. Multiplicity should be high. PIM, anom, d double prime over sigma. So you can see the values are developing to something like 0.8. Well done, this data set is processed well. But also there is significant anomalous signal here. So this is a sulfur set data set, very good one. If you have done the tutorial, you may have seen statistics like this because that's the tutorial case. And here's CC half, and it drops below 25, about here, at 2.3 angstrom. So that might be where we want to cut the data. But you could also go by d double prime, and by d double prime I would possibly choose 2.1. Or if nothing works, you can try different resolution cutoffs. Sometimes only one of them works. So I usually vary the values over a range. So that brings us to SHELXD. And I'm going to talk for a moment about the algorithms in SHELXD. So SHELXD was originally written for small molecule crystallography. This program has never been developed to be a macromolecular substructure finding program. It was developed for direct methods. It has then been abused by Isabelle Lauzon to solve the substructure in macromolecules, and then became very famous for this. And today, SHELXCDE are also known as the macromolecular part of SHELX. It uses dual-space direct methods. I'll come back to that in a moment. And it utilizes the triplet equation and the tangent formula. It also uses Petersen seeding. Now, the triplet equation is a fundamental equation in direct methods that makes connection for 3 different reflections for their phases. So it enables to find the phase of a structure factor from 2 other structure factor phases. And it's not an exact equation. It's a statistical thing. So let's see if we can do this. I actually brought an example. So you can follow what I mean by this equation. So the equation is phi HKL minus phi H prime K prime L prime. So these two should be 2 strong reflections equals phi H minus H prime K minus K prime L minus L prime. Now, if we assume that this HKL is 1, 2, 3 in our data set, and that one is 1, 0, 1, right? Then this one would be 1 minus 1 is 0. 2 minus 0 is 2. And 3 minus 1 is also 2. So this would be 0, 2, 2. That's the reflection we are looking at here. And if the phases would be 62 degrees for this one and 105 degrees for this one, well, that one would be minus 43 degrees. And it's modulo 360 degrees, so it's actually 318 degrees, if you want it as a positive number. And that is how we can calculate from those two phases a third phase. That's how it works. So once we have a starting point and we have phases for some reflections, we can calculate others and then expand this network and calculate more and more phases. Because it's a statistical measure, it only works for strong reflections. It's important to keep in mind here. There is a general formula which can be derived, but I have no time for that today, but it can be derived from the triplet equation. And that's the tangent formula. And that's the general formula to find the phase of the sum of complex numbers. These statistical methods only work because electron density has certain features. For example, it is never negative. It is not usually 0. And atoms don't tend to lie on top of each other. Atom separation is required for these equations to be true. So we have these equations, but we still need a starting point. Where do we get a starting point? Well, we could just assume some, just like I did, some random numbers. And if we start often enough from different random numbers and then expand the phases, we may end up one day with the correct substructure. And believe it or not, that was the usual way in, for example, Rantan, and it's still a way that is supported by SHELX. You just do so many trials that you cover these possibilities. But the better way to do this is actually to start with phases that are already consistent with the interatomic distances, which we know from the Petersen map. We saw that last week, that the Petersen map gives us all the interatomic distances in the substructure. We just don't know how they are relative to each other. And we can start with positions that are consistent with that, convert to phases, and use these as starting phases, which is called Petersen seeding. And the SHELX keyword for that is PETS, and it's a default keyword. So in dual space direct methods, you use these equations to expand your phases. And then you go to real space, and you prune, and you keep only the highest peaks in the anomalous map. And you take these atomic positions, calculate new phases, and go back. So because we are iterating between real and reciprocal space, it's called a dual space direct methods algorithm. And yeah, on the bottom of slides, the slides will be available from my homepage today evening, are some tips that are related to that. But how do I actually, so I now know how SHELXD works, but practically, how do I know it has worked? Right, I've run the program, but how do I know that actually I got a correct substructure or the substructure could be good? And what do I do if it doesn't work? SHELXD calculates quality indicators again. Again, a CC. CC all is the correlation coefficient between the normalized structure factor differences. So these are the intensity differences. They have been normalized, and I compare them to the atomic positions in my substructure. I know what, from this substructure, I know what intensity differences I expect, right? And then I compare this to the actual intensity differences. And the two should be correlated if the substructure is actually correct. Now, because that's more or less the information we put in to find the substructure, this is not a very independent criterion. The other criterion we can use is we can take all the weak reflections that we didn't use in direct methods and look how their correlation coefficient is with the substructure. And that's CC weak. And CC weak, therefore, is slightly more independent of the substructure search than CC all. In order for a substructure to be good, both of them would need to be high. High CC all, high CC weak. Now, because both of them need to be large, we can just combine them by summing them up. And CC all plus CC weak is something called CFOM, combined figure of merit, which anyone who has ever manually run SHELXD will have seen. And when we plot CC all against CC weak, we also often see a clustering. So there's a clustering for low CC weak and CC all solutions, and there is a clustering for higher solutions. if you see this kind of clustering, very often that means this is a correct or partially correct solution. But the C-form value itself varies for different data sets and different experiments. So you need to build up some feeling for it while you are trying to solve the substructure. And clearly, this is not ideal. We would like a better indicator for whether a substructure is correct or not. Only we don't have one. So if anyone here can come up with a better indicator, that would be more than welcome. So another indicator is a clear drop in marker atom occupancy. So you get your substructure, and SHELX will calculate an occupancy for them. And if the occupancy is high, 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 and then suddenly low, 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 that's usually an indication that actually that has worked, and the substructure might be correct, or at least partially correct. However, if that doesn't happen, that's not an indication the substructure is wrong. It might be that you did not give enough atoms to search for. You need to specify a number of atoms to search for. If you've got 20 anomalous scatterers, but you only searched for 10, SHELX may only give you 10 or 12, and then all the occupancies will be high, and this criterion will not hold. Also, the number of atoms you search for is actually a crucial parameter. So resolution cutoff is crucial, and also the number of atoms to search for. But how do you know? It should be 20% within the true number. But if you do an iodine soak, how are you going to know how many iodines to expect? Luckily, there's a formula for that. So you take the number of residues, amino acid residues in an asymmetric unit, and divide it by 15, and that's a good starting point. But I would again propose to start several runs with different numbers of atoms to search for. And then you have RIP, radiation-induced phasing, and there you have no sharp drop whatsoever because all atoms are susceptible to radiation damage, right? So yeah, you would expect that their signal is just wavering off. But a good starting point is the number of disulfide bridges because they get split first, so they will give you peaks. And then there is sulfur set, and sulfur set is kind of a problem because the disulfide bridge is about 2 angstrom long. Now, if you have decided on a resolution cutoff of 3 angstrom, all your disulfide bridges will fuse into one. There are 2 sulfur atoms, and they will fuse into one blob. Because at 3 angstrom resolution, you're definitely bigger than these 2 angstrom distance. So you need to search in this case for only one peak. And that peak will be slightly elongated, which you can specify with the keyword diesel, which should have the number of disulfide bridges following it. If you decided on a resolution cutoff of 1.5, you should search 2 peaks because your sulfurs will give you 2 distinct anomalous peaks that are separated. So this is a little bit tricky. And unfortunately, it doesn't become easier by the fact that the new CCP4 GUI has decided to change this idea. So you need to click on help to know what it does. Another thing is, if you have disulfide bridges in such a high resolution, you will find many pairs of anomalous peaks, one for each disulfide bridge. So if you look at your substructure geometry in COOT, you could already know from this that it worked. If you use something like a magic triangle, which has iodines, 3 iodines, and you see a triangular shape in your substructure, you know the substructure search was successful. You can compare substructures if you already know perhaps part of your substructure using Sitcom or Phoenix Emma. But the ultimate indication is to run density modification and to actually get an interpretable map out of it. So if you're unsure, just proceed. And then at the end of SHELXE, you'll hopefully be able to tell whether it worked or not. If it doesn't work, vary the resolution cutoff, vary the marker atom number, do a lot of trials. Even starting from Patterson seeding, we need a lot of trials. So I routinely use 60,000, and 500,000 might be necessary. There have been several structures which would only solve after 100,000s of trials. That is particularly true if your data were problematic. I had one case where the beam had hit the Pilatus detector between panels instead of the beam stop, and we could solve this, but only in try 600,070 something. And in total, I ran for this structure 80 million trials, which takes 2 weeks on a cluster. But we solved the structure, and it became a nice paper. And you can use MRSAT, which I'm going to talk about after talking about SHELXE. SHELXE improves the phases from the initial phases calculated from the substructure and the alpha angle. It resolves the handedness of the substructure, about which to this moment you had no clue. It can use free lunch, which I haven't talked about yet. It uses the sphere of influence algorithm, which I have already been talking about, and I'm possibly going to skip it. The solvent content is crucial, because the density modification works exploiting that the protein is peaky and the solvent is flat. And you should use NCS if you can, if you know it already. The free lunch algorithm is a very strange thing. Imagine you have measured an incomplete data set. You take the reflections you did not measure, the ones that are missing, and you put for their intensity numbers that are just somewhat plausible, but generally just guessed. There's no basis except they fit the general statistical distribution for intensities. Now, this should not really improve things, but amazingly it does. And if you can even expand if you have good resolution, 2 angstrom, you can, for example, say I free lunch to 1.8 and just expand the resolution of your data for the purpose of phasing by guesses of what the intensities could have been. Now, why would that work? One good answer is 0 is a bad estimate for something you haven't measured. At least the guessed values fulfill statistically the needs. One is, do you remember? No, I didn't show that here, but there's Fourier ripples. So Fourier truncation effects get minimized if you don't have a sharp edge. And also, the phases are the major influence. I don't know if you've seen Fourier cats and ducks, but the cat dominates with the phases. The picture, while the duck with the amplitudes is not so good. So the phases are the major influence. Perhaps the intensities are just not so important. And here's a rather spectacular example. This is a structure where one wedge of data had been missing because they assumed the wrong space group or the crystal died. Incomplete reflections were measured to 1.3 angstroms. The map is very hard to interpret. It's very difficult to see what's what here. After free lunch and expansion to 1 angstrom, the map looks beautiful. So you actually can get this kind of improvement also from auto-building. But there are cases where you can't auto-build. For example, if you're working with RNA and DNA. And in this case, I would still advise to use free lunch. Also, free lunch to your native resolution, the resolution of your data set, just filling up the reflections that haven't been measured, is a default in SHELXE. And you need to switch it off if you don't want it. Newer features also include marker atom substructure optimization, MR and MRSAT facilities, and the SAT backbone tracing. So SHELXE, given your resolution is better than 2.5 angstroms, can be told to search for the backbone. So it tries to build a backbone through your density. Why we do this is to get the best experimentally phased map. SHELXE is not an auto-building program for constructing your structure. You should use an auto-building program for that after running SHELXE, like War Buccaneer or other programs. And generally, a structure that can be traced is a structure that is solved. So if at 2.5 angstrom you've got a CC of the traced backbone against the data of more than 25%, your structure is solved. The opposite is not necessarily true, but mostly this holds as a rule of thumb. So how does it work? First, we do a peak search in the electron density map. Then we position a helix or tripeptide fragment. We extend it at both ends by 2 amino acids. Then we do a simplex optimization of the position, and then we delete the third residue. Then we do that again and again and again, expanding the chains as we go as far as we can. At the end of the electron density, where we can't trace any longer, we do a figure of merit calculation for the chain, and we splice if necessary, because we could have had one trace start here and one trace start here, and they would be lying in the same density, so we need to splice them together. That's what it looks like. So you can see it's a polyalanine, so there's no side chains. And the density usually gets vastly improved. But one of the major advantages of this is that we can actually automatically decide whether it worked. So to find whether SHELXE worked is a map that looks like protein. If you see the map and you think, I can build in that, well, SHELXE obviously has worked. You should, though, always choose the right hand. Connectivity should be high. That's a value that it gives to you. Map contrast should be high, because protein map is usually connected, and usually there is strong contrasts. And, yeah, you need the correct hand. That's important. If it doesn't work, if you have high solvent content, you want to have more cycles of density modification. If you've got high resolution data, better than 2.5 angstrom, you can do a backbone trace. If you've got high resolution data for DNA, RNA, you can do free lunge. But if the density modification doesn't work, but you're trusting the substructure because it looked good, try to raise the solvent content by 5 or 10% and try again. Ensure both enantiomorphs of the substructure have been tried, and optimize the substructure before density modification, either using the -Z optimization in SHELXE or using, for example, AutoSharp or Phaser EP, because that may also make the difference. So we had this normal workflow. Now, if we take SHELXE, we can do something else with it. We can take initial phases, not from a substructure, but from a molecular replacement model. So we feed the MR solution in form of a PDB file that has been renamed to PDA into SHELXE. And then we do the normal data preparation with SHELXC. But since this is not experimental phasing, that's just really only the normal data. We feed both into SHELXE, and that helps us to improve the phases from the MR solution, to expand the map, because often MR solutions are, even like good solutions, can only be limited to a certain part of the map. And also we remove bias from the search model used in molecular replacement. But you need very high resolution data, better than 2.1 angstrom. So this is not a method that you can use if you've got a low resolution structure. But I want to show some rather exciting examples. So this is a domain from the PDB. It's got 1 angstrom resolution. It's got 82 residues. This is a model placed by Ample. It contains 3.5 residues. So that's very little atoms. TFZ in Phaser was 2.5. LLG was 42. I would say we wouldn't be so sure this actually solved. Now, if you run this through SHELXE, this is the autotrace. It contains 86 residues, possibly having overtraced on the end. And the CC of trace against native data is 32%, which means the structure has been solved. So what does this mean? The toehold we need to start is sometimes really small, in particular at high resolution. And that can be exploited. For example, it is exploited in Archimboldo, where a small fragment is placed and then expanded with SHELXE. And also, SHELXE can give a quick indication of a correct MR solution. It needs no sequence, and it can be a step between MR and autobuilding. However, if you can't use this for your MR solution, it does not necessarily mean the MR solution was wrong. In particular not when there were a lot of beta sheets, because autotracing works a lot worse with beta sheets. The next example is 1.9 angstrom and has a little bit more residues, 1,500 residues. It's PRP8. After MR with MolRep, they got a working R of 45 that would not drop. After SHELX, I got a CC, or they got a CC of 32%, and they got 1,222 residues, which oddly enough were not in the same region. So if we go back and look, that's the original thing, and they deleted most of the original MR solution and traced mainly in this area. That's what the map looked like after molecular replacement. You can see that the protein was rather well defined in the area where the search model had been placed, and there were some structures here that they couldn't fit something in. And then after SHELXE, the map looks like this. And that actually made a difference for PRP8 to be solved. Now, there's, of course, the middle ground between experimental phasing and using SHELXE for MR, which you can use at 2.5 angstrom, which is to use experimental data, preferably SAT for MR SAT, feed them into SHELXC, take an MR solution, and basically jump substructure search. Consequently, doing MR SAT. If you want instructions, by the way, just type SHELXE, enter, and the program will give you instructions on how to do this. Yeah. That's more or less all I wanted to say today. I have 2 extra slides about radiation damage, but I'm only going to show them if someone is particularly interested in RIP phasing. So we have been going through SHELX. We've seen that SHELXC can be used to decide whether the data are good enough to start and also where to cut the resolution. We've looked at SHELXD, which does a dual space direct methods algorithm to find the substructure. We've looked at SHELXE, which can density modify, but also use free lunge and polyalanine backbone traces, and has facilities for using molecular replacement structures or to do MR SAT. And as I said, next week we are going to look at twins. Any questions? Sorry, he was first.
I would like to go back to this about disulfide bridge.
Mm-hmm.
You said that resolution cutoff is very important and number of atoms is important. How do I know, starting the SHELX, number of disulfide bridge?
You look at your sequence, and from the sequence, you'll at least know the number of cysteines. And then you have to have an educated guess at how many disulfide bridges that may form, or you look at homologous structures. But if you are not sure, you need to try different numbers.
So this is complete guess?
No, because you should very often you know from the structures that are similar, and from the reductive oxidative state, and from the sequence, how many disulfide bridges to expect.
For the free lunch, is it only valid going, for example, for high resolution atomic, or if I, for example, data 3 angstrom resolution? Can you use free lunch to go 2.5?
No. You cannot, because the phases are not good enough. But you can use it to fill up to the completeness. And you could use it, but the question is how good would it perform? So you can try, but usually at low resolution it doesn't perform so greatly. While
it's not the default.
It's the default to free lunch the data to the resolution of the data set. So if you get 2.1 angstrom, it does free lunch to 2.1 angstrom, hence filling in all reflections that have not been measured. Yes?
The triplet equations rely on your strong anomalous differences.
Mm-hmm.
So if you have outliers in that kind of regime, I guess that has quite a
Yes,
Do you have any
absolutely.
recommendations for trimming outliers prior to?
Use a good mask in integration. This is really crucial. You need to block the beam stop and everything in its vicinity. Look at the plots of the outliers over your detector surface. I usually generate them with setups, which is Bruker proprietary, but there is also an option in Aimless to do so. And make sure your scaling program actually did what you think it did, cutting off your outliers. And you need to use anisotropic scaling. That's also very important, but usually done automatically.
Are there any metrics in SHELXC output that would suggest that that's an issue?
It is very hard to tell once the data have been processed. This is really something that needs to be looked into in integration and scaling, and at this point needs to be resolved. But when I get data sets that mysteriously only serve with one half of the data but not the other, I usually look at the low resolution range where the strongest reflections are and look if there's something that really strikes me as a rather unusual outlier in the difference.
Yeah.
Yes?
Does the triplet equation, does that have a rigorous mathematical background, or is it just something that you notice is
No,
the case?
it has a rigorous mathematical background. This is actually, so this research goes back to Sayer and Karle and Hauptmann, and there is good evidence. It's not something that was just noticed, it was something that existed. So actually Karle developed this separate from crystallography, and then his wife Isabella proposed to use it for phasing, and then it was applied from mathematics to crystallography. And I once had the opportunity to talk with both of them about it. It was rather fascinating to hear how it occurred that it might be useful to solve structures. So it comes from mathematics.